Okay, so we're going to look at a two proportion test here. So what I want to imagine is a situation where you have two populations. Okay, so like where this might happen is like if somebody's testing something at like trying something out at a school or a set of school or a school district, you might like find like a school district that's very similar to the one that you're working with that has a similar population and compare the results of the two. So what we're going to do is we're going to say we have one school district in Ohio that has a total of around 5,000 fifth graders, and we're going to take a school district in Maryland that has around 4,500 fifth graders. And we're going to do something. We're going to apply a treatment to the Ohio school. So we're going to have all the fifth graders in the Ohio school participate in a certain program, but the students in Maryland are not. We're going to see if there's a significant difference between these, right? So we're going to, after we're done with the treatment, we're going to take a sample of 100 fifth graders using a simple random sample in the Ohio school. We're going to take a sample of 150 fifth graders using a simple random sample in the Maryland school. And we're going to say when we did this in the Ohio school, 68 of these fifth graders showed growth in the way that we wanted them to. And in the Maryland school, 104 of these fifth graders showed growth in the way that we wanted them to. Remember, only the treatment was given in the Ohio one, right? So we want to know if there's a significant difference caused by this treatment in the population. So here, the proportion of the sample that had the characteristic was 68.68, and here the proportion of the sample that had the characteristic was 0.693. So whatever this treatment was, it seems to have actually only caused growth. It actually seems to have caused growth in less of the sample in the one in Ohio than the one in Maryland. So let's look at this and say, I want to first create a confidence interval, right? So my confidence interval has to meet three criteria. We have to have a random sample, which is what we met. We have to create a 10% criteria, which if I look at this, my sample 100 is definitely less than 10% of the 5,000 in the Ohio sampling. The 150 is less than the 10% of the 4,500 in the Maryland sampling. So we meet the 10% criteria, so we get a sense of normalcy from that. And then we want to do large counts, and you have to deal with large counts in four different ways. You have to take the large counts for the p hat 1 and the n one, so that's going to be 0.68 times 100, and that is 68, which is clearly larger than 10. And then I got to do the 1 minus p hat, so that's going to be 0.32 times 100. That's giving me 32, which is larger than 10. And I got to take 693 times the 150, which is going to give me like 103.95, which is bigger than my 10. And then I'm going to take, what do you call it, the 1 minus that, 1 minus 0.693. Let's see, I don't know what that is off the top of my head. Let's try to figure that one out. That's 0.307 times 150, which works out to be 46.05. So all four of the large count conditions are met. They're all bigger than 10. So what I do is I have to create a confidence interval. So we'll look at how do we do that. Okay, so my confidence interval here, remember, is now going to be like p hat 1 minus p hat 2 plus or minus the relevant z star times the standard error. Okay, so the z star here is determined by my degree of confidence, which I'm going to make 95%. And from some earlier work using invert norm, that means my z star has to be about 1.96. So my p hat 1 is 0.68 minus my p hat 2 is 6.93 plus or minus my z star, which is 1.96. And then if I multiply that by my standard error. So standard error here, you have to remember you have to like break back to the variance and then build up. So the standard error here becomes 0.68 times 0.32 over 100 plus 0.693 times 0.307 over 150, which works out to be roughly 0.05995. So if you take that interval, what you're going to end up here with is going to be like negative 0.013 plus or minus 1.96 times 0.05995, which on the low end is going to give me around 0.13, and on the high end I'm going to get around 0.10-ish. Okay, now there's going to be some rounding error in here, and there's some issues with significant digits, so we're just going to hang that there. Now, it's highly unlikely that you're actually going to do this by hand. So let me go into the calculator here, and I'm just going to kind of clear stuff out a little bit. And I'm going to go stat, tests, and I'm going to go down to a 1 proportion, 2 proportion, z interval. I'll put my data in, right? So for proportion 1, I got 68 with a sample size of 100. The second proportion, I got 104 with a sample size of 150. So I calculate that, and if I look there, I got that negative 0.13 to positive 0.10 interval, and all the recording data that I expected to get. So my this is my confidence interval, right? So you take a look at the notes. The formulas are all there for this kind of stuff. So let's look at what it looks like for a significance test, right? So the first thing you got to recognize is here the standard error for the significance test is going to get calculated a little bit differently. They're going to use what they're going to call a pooled standard deviation or standard error here. And what you're going to have to deal with is, instead of the two p hats, the p hat 1 and the p hat 2, you're going to create a pooled p hat. All right, which is essentially x1 plus x2 over n1 plus n2. So this is like as though you had made it a single population. So in our case here, this is 68 plus 104 over 100 plus 250, which is going to work out to be 0.688. Okay, and the one minus that p hat is going to be 0.312. Okay, so that's what we're going to work with when we're dealing with the significance test. So we're going to assume that these guys are coming from a single kind of population that gets pulled together. Okay. All right. So in the significance test, you need to have your H null. The H null here is just always going to be that the difference between the two is 0. Okay, so this is basically another way of saying that the two populations are equal. And the alternative, more often than not, is going to be that these things are either going to be somehow less than, greater than, or equal to. Now, like in our example with the two school districts, not equal to rather, we're going to use the not equal to. We're going to deal with this as though we want to see if there's a significant change by applying the treatment to the Ohio district but not the Maryland one. Okay, so again, we got to set an alpha, right? So I'm going to set alpha as 0.05, and we got to create a test statistic, right? So we still managed to make sure that we have our random or our criteria met, right? So we've checked the random, We've checked 10%. We have checked large counts. All of these are in place. So for our test statistic, our z-score is literally going to be p hat 1 minus p hat 2 over our pooled standard error, right? So the pooled standard error is now going to be square root of p hat times 1 minus p hat over n1 plus p hat times 1 minus p hat over n2. Okay, so note these are p hats and not the p hat 1s and p hat 2s. So in our case, this number, if you kind of play it all the way out, is going to be like around 0.05981. So this is now going to become negative 0.013 over 0.05981, which gives me a test statistic of around negative 0.217, right? So this is saying that so let's think about what this looks like graphically, right? Graphically, I'm going to suggest that my mean is 0, right, from my null hypothesis. So I'm saying I am like negative 0.217 is my z-score, but I want to be as extreme or more extreme than that in either direction if I'm doing the two-tailed test. So I want to be 0.217 here. And if you invert the norm, right, on this, you're going to find that this is about 0.414, which means this is going to be about 0.414. So my p-value is the probability of being in either of those zones. So 0.414 plus 0.414 gives me 0.828, which is now my p-value. P-value is 0.828. Okay, so if I'm kind of thinking this through, I set an alpha at 0.05. I have a p-value at 0.828. Well, that's a really large p-value for this situation. So it's highly unlikely that the difference between these proportions is statistically significant. Like one being at 68% and the other one being at like 69.3 is really not that statistically different. Okay, so let's play this out in the calculator. So if I go to stat tests, two proportion z test, I've already got the data in there, right? 68 out of 100, 104 out of 150. I'm going to do the not equal to, and I'll go ahead and calculate. And there's that 0.82. Now it's giving me a 0.823. I calculated a 0.828. There's probably some round error there. My z was like 0.214. Theirs is like, or 217. Theirs is like 0.222. There's something going on there with some of the rounding errors, because you got to remember, like, this 0.693333 is like that, and we're doing, so it's going to get close, and close enough that you can make a judgment, right? So we're going to look at this a little bit deeper in class here, but I wanted to do a preliminary walkthrough as part of your homework, and then we'll kind of sink into this. Usually when you're getting these like two proportion questions, they tend to line up with stuff that you can do with the calculator fairly easily. So we'll look at it from there. I hope this is helpful.